We were talking about finite automata last time, and we had a look at deterministic finite automata. What are these good for? I mean, they're sort of fun to play with, right? But some people that really, I mean, they cannot do any sort of theory without seeing the practical application. So let's say a few words about this. When you write a compiler or any sort of programming language, there are some components like which are sort of lexical, which we need lexical analysis for, like what is an identifier, what's a number, what's a comment, and so on. This is a low-level structure, and this is done via regular expressions, finite automata, and so on. So that's one of the things they're good for. Yeah. Another thing is actually regular expressions, which are, we will see, related to automata. We haven't seen this yet. They are useful to describe patterns in text. If you want to write something like text processing, or if you want to write an editor script, yeah, to do something, we're using regular expressions, and they are translated into automata. More practice? No, let's go on. Let's go on. I have some more. Now we're going practical. Yeah. So another one is protocols, communication protocols. They're often described via finite automata. It's a good thing. And then finite automata are sort of the entry drug, so to say, to sort of formal description of computation, which do play a role in theory as well as in applications. So, okay.
Good, practical
Done.
stuff. Tick. Back to the theory.
Okay, yes, so today, last time we talked about deterministic finite automata, and I drew a few and we played with them. So, I mean, this is on this other video, and we don't have to go through this again. What I wanted to do today is another thing, it's non-deterministic finite automata. And what are they? We will see they look very similar to the DFAs, but they're basically magic machines. Whereas for a DFA, you always are in a state, and then you send some input, you go to a different state. For the NFAs, there is maybe a choice. You maybe go there, or maybe here, or you may be going nowhere. Yeah, and the magic is that an NFA will always make the right choice. Yeah, if there is a way that it could accept the word, it will make this choice. Yeah, so they're really magic machines, right? So we're going. I mean, they're not
presumably
just,
if you get them right.
No. I mean, yeah, they're magic. Okay, yeah, but they're magic in always guessing right when they run, right? So this is in general actually the case with non-deterministic automata. I mean, there are other kinds of non-deterministic automata, like push-down automata or Turing machines. They can be all non-deterministic, and the idea is they always do the right choice. It's a bit magic, right? And you may ask what are they good for again? Yeah, because the DFAs clearly we can implement, we can run, but the NFAs they seem to be a bit, or the non-deterministic automata seem to be a bit sort of fancy in like you have to have enough magic to be able to run them. Yeah. The point is that they're actually, first of all, in the case of the NFAs, we will see we can translate them into DFA. That's not always possible for other automata. It's not always possible, but in this case we can actually translate them. And the non-deterministic automata, they're sort of in between the more sort of abstract description of languages, yeah, and the actual implementation. So they're like a thing in between. So for example, when we look at regular expressions, we can translate them first into non-deterministic finite automata and then next step into DFAs. But they're sort of in between. So they're useful as in-betweeners. Yeah. So this example, so we're looking at a language of words over some alphabet. So the alphabet is this time is 0, 1. So we're looking at sequences of 0, 1. And the language I'm going to describe as a language so that the penultimate symbol of the word, of the string, is 1. Okay, let's play the game. Let's see whether Sean is a good automaton.
I've been practicing.
Very good. What about 1, 0? Is it in the language?
Yes.
Okay. What about 1, 0, 0?
No.
No. Okay, very good. What about 0, 1, 0?
Yes.
Very good. And what about 1?
No.
No, it's not. Exactly. Okay, very good. I think I can hire you as an automaton or something, you know. Okay, so let's build. Okay, how do I do this? I just fold it over. Okay, so let's build the automaton. So, as we have seen already, the automaton, they have little squiggles, which are states. Well, start, I call the state 0. And I say it's my starting state. So I put an arrow in. And now I say, when I see a 0 or 1, I stay in this state. Okay? But now if I see a 1, I get sort of excited because maybe I'm going to win. And then I have another state. Whatever comes here, I go into this state. And this is my final state. Okay, so that's an NFA. And why is it an NFA? Okay, so first of all, we have, when we're in the state 0 and we see a 1, we could go here or we could go here, right? So that's a bit weird, right? And then, when we see a 1, okay, with 0, 1 we go here, but then what happens here? What happens if we see anything? There's no transition. So it's not a DFA, yeah, for two reasons. So one reason, in this case we have got two options, and in this case we have no options. But let's see whether we can run this automaton. And you need a bit of investment to play with NFAs, yeah. So how does this work? So I'm simulating an NFA by putting coins on the states. And you may remember that the DFAs I did with my finger, but here it gets a bit more complicated. So let's say we want to do 1, 0, see what happens. So 1, 0. We are here, so we put a coin on the initial state, or actually an NFA can have several initial states. So we have to put all the coins on all the initial states. This one has only 1. Okay, and now we see a 1. So this one goes here, but it also goes here. So we are like in two states now, right? We are in state 0 and state 1 at the same time.
Like a superposition.
Yeah, super quantum, right? And now, okay, we have read this, and now we read the 0. So what happens is 0 and 0. And we are finished, and we have a coin in the final state, so hence it's accepted. Okay, let me do 1, 1, 1, okay? Which I didn't ask previously, but it just occurs to me that's a good example, okay? We start with this coin, then we have a 1, so we go here, right? And now we have another 1, so yeah, this coin stays here, this coin goes here, and this coin goes here, right? So we are finished, and we have a coin in the final state, so it's accepted. No surprises. Shall we do a negative one? What about 1, 0, 0? 1, 0, 0. Okay? So we start with the coin on 1. So now we read the 1. So we go here and here. Now we read the 0. 0, 0. And now we read another 0. This coin has nowhere to go, so we lose it. It's really a game of money. You can lose money, you can win money, but you can lose. Stays where it is. And we have no coin on the final state, so it's not accepted. So this is a finite automaton, and that's why we run them, right? With coins. But the idea is that the coins sort of represent all the states we could be in. Now we can translate an NFA into a DFA. Okay, so here the idea is that we have a DFA where the states are sets of states. So for example, what we start with is a state which has only the set 0. So now, if you have a coin in state 0, what we do is we define a DFA which tracks the configuration of coins, basically. Yeah. So if we have in state 0 and we see a 0, then we still have just one coin and 0. So that's this one here. Or if we see a 1, then we all of a sudden have 2 coins. So we have a coin in 0 and 1. So we go 0, 1. Okay. So now, let's say we are in 0, 1. What happens? If we see a 0, what happens? If we see a 0, we stay here and we go here. So we are, after 0, we are in 0, 2. But let's stay again. If we're in 0, 1 and we see a 1, right? If we're in 0, 1 and we see a 1, then these go here, but because we have a loop here, we go into 0, 1, 2. So if we're in 0, 1 and we see a 1, we're in 0, 1, 2. We are not finished. We have to get transitions for these as well. So what? Let's again. We are in 0, 2, and we see a 0. What happens? If you see a 0, this one is lost, but this one stays where it is. So we are back to the state where we only have a coin in 0. And what happens if we see a 1? So let's reset. We are in 0, 2. We see a 1. Then this coin disappears, and here we have 2 coins. Right? So that means if you see a 1, I hope I didn't make a mistake here. Okay, so here we have 0, 1. So we have to see if we have 3 coins, 0, 1, 2, and we see a 0, what's happening? This stays where it is, this goes here, and this is lost. So we are 0, 2. So if we see a 0, we go to 0, 2. Now what happens if we are 0, 1, 2, and we have a 1, we lose this one, and these all go like this. So if we see a 1, we stay to itself. Okay, so we have to mark initial state. So the state where we put the tokens and the coins or the initial states is this one. And then we have to mark the final states. So the final states are any state which contains a 2, where there is at least a token, I say, a coin on the 2. And this is in DFA, right? Because we have one initial state, and we have always we know always what's happening because we know what happens to the coins. Mm-hmm. And this is a famous construction, it's called the powerautomaton. And it shows, I mean, hopefully the idea is clear, that we can translate any NFA into a DFA, and the DFAs are easy to run, okay? Now why is it called powerautomaton? Because the states here are sets of states. So it's a power set. And in this case, it's quite harmless. We start with 3 states, we have 4 states. But in general, it could be an exponential blow-up, because with 3 states, we actually have 8 possible states, 2 to the 3, because there are 8 possible subsets. And there are lots of states which are not reachable, which we don't have to draw. So another 4 states which you don't have to draw because it can never be reached. But in principle, you can have automaton which blow up like this.
So it's doable, but not always practical.
Yeah, exactly. It's not feasible. Okay, shall we go to do some Python hackery?
Let's do it, yeah.
Okay. So here we have the code from last time, which was a code for DFAs. So we had an init function, a printing function, and a run function, and we have some examples. Okay, I'm going to do the NFAs in the same file because there's going to be some interaction between the two, right? We want to translate NFAs to DFAs, actually also DFAs to NFAs, which should be easy, but still we have to do a lot of work. Okay, so we define a class NFA.
Is it that certain problems are only able to be done with an NFA to start with, and then you translate it, or?
It's certainly much easier. So if you, for example, you say I want to recognize a fixed string, yeah, then to do this, to construct it, and DFA can be non-trivial because if you
think of all the possible.
So it's much easier to construct the NFA. And in principle, you can translate it. Yeah. Right, okay. Yeah, especially, as I say, if you come from regular expressions, then it's quite straightforward to construct for every regular expression an NFA, and then do the DFA, but it's not so obvious how to construct directly a DFA. So
and in terms of running this computationally, not on a piece of paper with coins.
Yes, we're going to look at it.
Yeah. So we look at it. Is it easier for the computer to do the DFA?
Sure.
As well?
Yeah, much easier. Yeah. Yeah.
Okay.
Actually, DFA has got a linear complexity, whereas for an NFA, it's first of all not clear. I mean, it turns out after translation, it's also linear. But okay, the init method for the DFA is very similar. The difference is that for the initial state, we don't have not one initial state, but we have a set of initial states, and the transition function delta now becomes the transition relation, because we don't always have function given a state and given an input. We don't have one next state, but we have a set of next states, and this represents a relation. Right? Okay. Let me just continue a bit. The printing function is quite easy, so nothing exciting, but let me first do my example automaton. Okay, so I call it N0. So what we have to say, we have to give the set of states, 0, 1, 2, the set of symbols, which is 0 and 1. And now we give this transition relation, and that's a bit more interesting than before. So we assign to any combination, every combination of a state and an input, a set of states. So here, for example, the set of state is 0. If we are in 0 and we see a 1, then we could be in 0 and 1. If we are in 1 and see a 0, then we can only be in 2, and if we are 1 and 1, we can only be in 2. So first of all, we haven't really described what happens for every combination. So this is implicitly for the combinations we haven't covered. So it's the empty set. And okay, then we have here a set of initial states, which is just 0, and a set of final state, which is 2. Okay. So what we now have to do is to define the run function for NFAs, and that's a bit more involved than for DFAs. We have to define a run function. This was very easy in the case for the finite automata. We just did a little while loop going through the symbols and just use the delta function to compute the next state. But here, okay, we have to compute the set of states at each step. And there's also the problem that sometimes we haven't defined the answer, and then it should be the empty set. Okay, so what I'm doing here is I have a function called doDelta, which constructs the set of the states looking up in this relation. But if there is no set, then it returns the empty set. Okay, and the run function, what it's doing, it starts with the set P as the current set of coins, is the set which is in the initial state. And then we have this while loop as before, but we have to compute the set of new coins. And what we do is we go through all the states which are in P in the moment, apply this delta function, and get the new states, and we take the union of all these. So we take the union of all these possibilities. And in the end, we set P to be this new state. And when we have processed the whole word, we say the intersection of P and the final state shouldn't be empty. Okay, so let's try to run this. We have here this automaton N0. So N0.run, what was our first example? 1, 0, which is yes. And now we do 1, 0, 0, and it is no. And what else? Oh, we want to do the string, which is just a 1, which is also false. Okay, just some test cases. Now, we have these two classes, NFA and DFA. First of all, every DFA should be an NFA. So how can we translate a DFA into an NFA? So I'm going to write a conversion method for DFAs called NFAs. To construct in an NFA, I have to construct this new delta function, and basically it returns a singleton set for any transition in the delta function of the DFA. And it also constructs the singleton set here, okay, for the initial states, because there's only one. So this translation is pretty easy. So using this function, we can translate every DFA to an NFA by just turning all these single states into singletons. And that's just how it looks like in Python. But I'm going to leave the other translation, the powerautomaton translation. I'm leaving this as an exercise, but I can provide the answer. So here, the idea is, if we have an NFA, we want to construct a corresponding DFA, and there we have to do this powerautomaton construction, which I've just described by example. So as I say, that's left as an exercise to the reader, but I can provide the answer if you get stuck. And now, let's try this one. A, B, A. Bad state.
Model system. These are like kind of engineering-y type things. This one is getting, creating, removing, providing, criticizing. So like, for some reason, these types of words